So we're going to look at the arc length formula for vector valued functions, or space curves. So R of t is something in the x component, something in the y component in 2 dimensions. And in 3 dimensions, of course, it would be something in all 3 slots, x of t, y of t, z of t. But let's consider how we're going to do this in 2 dimensions first. So let's look at a space curve. So here we go. Here's a vector valued function. Here's a space curve. We're going to break it up into very small pieces so that each piece is virtually linear. So we've done that. And each piece is change in S, change in arc length here, change in arc length there. So the total arc length is the sum of the change in arc length. And I'm going to just go ahead and pick one of these things and try to predict or guess what the change in S is going to be. So if I blow this up, call this change in S. What is the approximate distance of the change in S? Well, this part is change in X, and that part is change in Y. So what can we say for that? Thinking of Pythagoras, since this is a right angle, the change in S is simply going to be the square root of the change in X squared plus the change in Y squared. So what does that give us then for total arc length? It gives us this, which doesn't look like a formula you can use in calculus yet. And you'll notice our variable of interest here was t. So how do we introduce t into this question? That's going to be an important thing for us to think about. Well, what I can do is I can divide by change in t and multiply by change in t. Divide by change in t. And multiply by change in t. So this is starting to look like a Riemann sum that we can maybe use. That sum will become an integral. That change in t will become a dt. But again, how can we make sense of this? We've got a little bit of algebra work to do. So we're here, but now we can recognize that if we assume the change in t is positive, I can think of that as the square root of the change in t squared, which puts us here. Again, the way that I have that defined in terms of my picture, change in x was always positive. So that's not quite change in t. But normally speaking, we're going to go t from point A to B, where A is less than B. So it's reasonable to consider that the change in t on any interval will also be positive. But now that we're here, we're going to write this with a single radical. So what will that look like? So moving from 2 radicals to 1 radical, we get here. And then we're going to go ahead and make 2 different fractions rather than a single common denominator here. And do you think this is starting to look like calculus? Might we be able to think of this as a Riemann sum? Well, the next step should clarify that for you. Namely, change in x squared over change in t squared is change in x over change in t squared plus change in y over change in t squared. Times the change in t. So this is our total arc length. So how do we convert this from a sum to an integral? We think about this limit as the change in t goes to 0. So what will that give us? It would be better to say the total arc length is approximately this, but to actually go from approximation to equal, we should take the limit as change in t goes to 0 of that sum. So the limit as change in t goes to 0 of that sum is indeed a Riemann sum. So this is some integral over all t of what? Of the square root of what? Change in x over change in t squared as delta t goes to 0 will become dx dt squared plus dy dt squared dt over all t, or whatever t we're working with here. So that's our formula for total arc length in 2 dimensions. So it's not much work to go ahead and do the exact same argument for in three dimensions. So if I'm going from a point A to a point B in 3 space, well, what do we have there? So again, in 3 space, if I'm going from point P to point Q, what is that diagonal? We have the change in x in this direction, change in y in this direction, change in z in that direction. So essentially a similar argument tells me then that the change in s is simply the square root of the change in x squared plus the change in y squared plus the change in z squared. So doing the exact same argument, right, where we would go ahead and divide by change in t, multiply by change in t, convert it to a Riemann sum, we can see that in 3 space, the total arc length will be essentially the same formula. It will be the integral over all t that we're using here, which is the square root of dx dt squared plus dy dt squared plus dz dt squared. So that's our formula. So let us take a look at a question to see if we can use that to see what our strategy is to go ahead and find the arc length of a vector valued function slash space curve. So here we go. We've got r of t is 3 cos t, 3 sine t, 2t, as t ranges from 0 to 4 pi. What's r of 0? That's simply the point 300. How about r of 4 pi? What will that be? You get 308 pi. So if this were a straight line, it's not, right? It's a helix. But if it were a straight line, the straight line distance from 300 to 308 pi is actually very easy to determine because this is directly on top, right? They have the same x and y value. So the straight line distance is just 8 pi. Now, what is that approximately? Just so we get an idea of what we should have here. 8 pi is approximately 25.1. So what I have is not a straight line. I have a helix that is emerging from this vector valued function from 0 to 4 pi. So my answer should be something more than 25.1. Will it be a lot more than 25.1 or a little more than 25.1? Well, let's see. What do I need to do? What have we said? We have said that our formula was what? We said our total arc length S, that I'm going to use now, is what? Is the integral over all t of the square root of dx dt squared plus dy dt squared plus dz dt squared. What is that? Do you recognize what that formula has to be? Dx dt squared plus dy dt squared plus dz dt squared. What is that? Dx dt, dy dt, dz dt. This is simply the integral over all t of what? Of the magnitude of the vector dx dt, dy dt, dz dt. And that vector dx dt, dy dt, dz dt is the velocity, right? So we have one more way to think about this formula for the arc length of a vector valued function. It is simply the integral of the magnitude of the velocity, also known as the speed. So looking at our formula here, what are we going to get? What is r prime of t? It's negative 3 sine t. 3 cos t. We said our formula was what? We said it was the magnitude of the velocity or the speed. So we have the velocity here. What's its magnitude? What is the magnitude of r prime of t? Square root of 9 sine squared t plus 9 cos squared t plus 4. Well, this turned out nice, didn't it? We get the magnitude of r prime of t is what? 9 sine squared plus 9 cos squared is 9 sine squared t plus cos squared t. So it's 9 plus 4. So the speed is simply root 9 plus 4, or root 13. And what did we say our formula was again? We said this, right? We said dx dt squared, dy dt squared, dz dt squared, square root of dt, or the integral over the speed dt. So my speed is just root 13. I'm going from 0 to 4 pi. So that my arc length here will be s, will be the integral from 0 to 4 pi of the speed dt, which is the integral from 0 to 4 pi of root 13 dt, which is root 13t from 0 to 4 pi, which is going to be root 13 is 4 pi minus 0, which will give me 4 root 13 pi. And remember, we said the straight line distance was 8 pi, 25.1. So is this a little bit more than 25.1? Let's see. We have 4 times the square root of 13 times pi. And what do we get? We get 45.3. So quite a bit more than 25.1.